Welcome and thank you for joining us to the second Dry Scrubber Users Association webinar about circulating dry scrubber technology. I'm your current DSUA president, Jerry Hunt. For those of you who are joining us that's not familiar with DSUA, it's a nonprofit organization that was developed in 2008 with the intent to foster the collaboration and innovation for dry scrubbing solutions. Since 2008, DSUA has been holding annual conferences, but the development of these webinars has become something that's been a necessary evolution for DSUA in order for us to continue that mission in 2020 due to the COVID-19 pandemic. So getting right into today's agenda for the CDS webinar, we've got Mike Saracena of Rain CII, as well as Matthew Wilson of TVA. And for those of you that are logged into the live streaming, you should be able to see that you have the ability to submit questions through the Slido, and our moderator will be monitoring those questions, and we'll do our best to ensure that all the questions that are submitted get addressed during today's webinar. But please note that anything that doesn't get addressed, we'll do our best to follow up via responses after the webinar through LinkedIn, as well as email to the registration group. So the goal is to get any and all questions answered that are submitted through the webinar. A couple quick DSUA housekeeping items before we get into the content. Today's session is something that's going to be, the live streaming is going to be recorded. So anyone that, whether you have to log off early, someone that couldn't make it, or someone that had trouble logging in, please note that once this video is, the recording is completed and uploaded, it'll be put up on YouTube, and the link will be shared through the website as well as the LinkedIn page and emailed out to the DSUA mailing list. So there will be ability for future viewing opportunities. And if the content you guys see today is something that you have interest in looking through additional DSUA content, please note that DSUA has an archive dating back to 2008 for all the presentations that have been done over the years. And, by paying for a DSUA membership, you can get access to all those historical archives. So please visit the DSUA website if you have future interest to inquire further about the archives and a membership. And also, if you yourself have interest in giving a presentation for a future DSUA webinar, please feel free to reach out to us through the website as well as through the LinkedIn page, and we're happy to coordinate the following steps from there. Before we get into it, I think one important thing we wanted to do was acknowledge and thank our sponsors for today's webinar. Our sponsors always go a long ways to help continuing the DSUA mission, especially as a nonprofit, and they've certainly been instrumental this year for DSUA, as well as over the years they've been historic contributors to the dry scrubbing industry. So I wanted to acknowledge and thank those guys. Gecko has been, they've utilized revolutionary wall climbing robotic technology in order to do infrastructure inspections. So their robots and inspection teams, they've been using that technology to perform NDT inspections throughout the globe. So end users have the ability to perform routine inspections in hazardous environments, both quickly as well as safely, while simultaneously collecting data. Leckler, they've been designing and manufacturing spray solutions for air pollution control applications for over 140 years. So this includes nozzles, nozzle lances, valve stands, and mist eliminators. So whether you have gas cooling application, purification, desulfurization, or denitrification, reach out to Leckler. There's someone that can help you with that application. So in addition to technology, they also have a technical team that can help provide a highly reliable custom solution for your site-specific needs. National Filter Media, they were founded in 1906, so that makes them one of the world's oldest and largest provider of air pollution control and liquid filtration products. So while the industry has changed a lot since 1906, National Filter Media, they've still been using the same fundamental principles of working closely with their end users to develop trust, as well as a long-term partnership through their products as well as their customer support. Mississippi Lime, They've been around for over 100 years as a world-class producer of calcium products, whether it's quicklime, hydrated lime, or calcium carbonate. And they've been providing these products from one of the richest limestone reserves in the world. They've got over 12 plants and terminals to supply products throughout North America. So they've got high quality quicklime and hydrates that have been used as a part of multiple cost-effective solutions for a multitude of dry scrubbing applications. So again, thank you to these sponsors. And also want to acknowledge today's moderator and turn over to him for today's session. So today's moderator is Dr. Ian Saratovsky. He's a director of flue gas treatment at LAWAST. He's got a PhD in inorganic chemistry and environmental engineering from Northwestern University, as well as an MBA from Northwestern University's Kellogg School of Management. Previous to that, Ian did a fellowship in the UK at Oxford University, and he's got over 12 years of experience in air pollution control and wastewater treatments, with particularly around industrial process optimization. He's had his focus on new product development for acid gas treatment, for efficiency optimization, and as well as Ian's expressed that he's been passionate about his time he gets to spend in the field working with end users, whether it's a field trial or optimization and troubleshooting, specifically on DSI and CDS applications. So right now I'm going to turn it over to Ian to continue with today's session. Take it away, Ian.
Good morning, everybody. Thank you for joining us today. We'd like to get started and keep everybody on track and on time. Please do submit questions on Slido. We'll make sure that those questions get asked. And then I have a few questions I can ask as well. So today we're going to get started with Mike Saracena. Mike is a senior process engineer at Rain Carbon. Mike has a BS in chemical engineering and has worked at the plant level in numerous petroleum coke calcination facilities around the southeastern US and chemical facilities with a primary focus in carbon distillation all across Europe. He's primarily focused on waste heat recovery sections of these facilities, specifically improving the energy recovery and emissions units. He has worked with several DSI and CDS SO2 control systems, and today he's going to tell us about the CDS system at Rain Carbon.
All right. Thanks for the intro, Ian. Am I live? My screen?
Yep. You're ready to go, Mike.
Awesome. Thank you. Hello, everyone. So as Ian mentioned, I'll be going over two of our CDS systems that we have installed in the southeastern US region. I'll be telling you some of the just the basic operational parameters of the systems, some of the problems that we've had since commissioning, and some of the optimizations and improvements that we have implemented. So a brief overview and background on our process. Our primary process is the calcination of green petroleum coke into calcined petroleum coke. That's primarily a combustion process that off-gases SO2 and SO3, which is then scrubbed in our CDS systems. We have two CDS systems, both at Lake Charles and our Chalmette facilities. They have been operating for between 5 and 10 years. Combined consumption of hydrated lime is over 10,000 short tons per year. And we have Lawson wave feeders measuring lime consumption at one of our sites. The other one is a direct injection. So a little bit of background on the system. I can appreciate that this process flow diagram is a little bit small. The flue gas enters here, comes into the bottom of the reaction tower, where fresh lime and water is injected to cool down the process stream. Most of the reaction occurs in this reaction tower. The flue gas then continues into the bag house, where the spent lime at that point and scrubber ash is then removed. The flue gas then continues to the ID fan and out the cold stack over here. There's two recirculations, so the spent lime that doesn't get sent to the spent lime silo goes back into the reaction tower. And the flue gas that is clean is recirculated back into the entrance of the reaction tower. Both of these recirculation loops improve reaction efficiency. System operational theory. So the lime injection flow rate controls cold stack SO2 emissions to a certain concentration or pound per hour flow rate depending on the facility. So that's the direct feedback loop. The reaction tower outlet temperature, which is controlled by the water injection into the scrubbing tower, is dictated by either the corrosion or any material handling issues that we have depending on our facility. The spent lime recirculation valves control how much lime is recirculated back into the reaction tower, and those are controlled specifically by the reaction tower differential pressure, which we currently have set to 3 inches water column. The gas entering the CDS out of our economizers, which we have at both sites, is around 350 to 400 degrees Fahrenheit, depending on how long the boiler has had since its last cleaning. Our backhouse cleaning cycles maintain differential pressure in each module individually. So there's a high and a low pressure DP in each module, and the backhouse will pulse until the low DP is reached and stop pulsing until the high DP is reached. With respect to the water spray nozzles, we've never had any issues that we're aware of. We've never modified the design. We have not adjusted the pressure of injection. We really haven't gone anywhere near that process parameter. So getting into some of our lessons learned, immediately upon commissioning and probably for a few years after at Lake Charles, we had some fairly severe corrosion issues. Basically, the root cause was our operating reaction tower temperature was too low and either too close to the acid dew point or below the acid dew point, which resulted in some severe corrosion of our cold stack. So a few years after we commissioned, our entire cold stack needed to be replaced. And we also had decreased baghouse bag life. We didn't really see any severe duct corrosion. It was primarily focused on these two pieces of equipment. So, as I said, we root cause this by saying that the flue gas temperature was too low, so we increased it, and then we had to incrementally decrease it and optimize it as we saw a massive increase in lime use due to this increase of temperature. So what would we do next time? I would definitely recommend installing either an online acid dew point monitor or a moisture dew point monitor to measure the acidic nature of the flue gas. They're really not very expensive, and they would have saved us many hundreds of thousands to millions of dollars in corrosion costs. We also coated the inside of our cold stack with a corrosion-resistant material. Again, there's some question as to how well these materials work. I think the proper way to address this problem is to have some feedback on how corrosive the flue gas is via a monitor designed to do that.
Hey, Mike, we have a question from the audience. What is the temperature out of the CDS at Rain?
It's different at Lake Charles and Chalmette. Chalmette is 220, but that's dictated due to our environmental restrictions or permitting restrictions. Lake Charles, it's closer to 240, 250, and that's due to material handling issues that we have at lower temperatures. The flue gas at Lake Charles is a very high water content. At our stack, it's 30% by volume. And our thought is that high amount of water is causing material handling problems, especially at lower temperatures. So lessons learned, Lake Charles lime consumption optimization, as I alluded to in my last slide, when we increased the temperature, we saw our lime consumption increase that directly resulted in material handling bottlenecks as we could not operate the system as it was intended. So because we had to increase the temperature, we had inefficient operation and a high scrubber ash available lime index. So available lime is the percentage of unreacted calcium hydroxide in the scrubber ash or spent lime. And this is a good metric to use to say, how efficient is your system? Really, how much of the lime are you not able to react? And so that's a metric that we used consistently throughout our optimization of this system. So how the process went was we incrementally lowered the reaction tower temperature through trial and error while being conscientious of the available lime index and corrosion and trying to balance that really without any real-time feedback like an online acid dew point monitor would give you. So it was really an incremental trial and error based way to improve the system, which, maybe not necessarily the best way, but it certainly is the lowest capital cost way to improve the system, assuming you don't damage anything. So as I mentioned, we're using available lime index as our primary performance metric. What would we do differently? Certainly continue to analyze spent lime as a metric for scrubber efficiency immediately upon commissioning. It took us a few years to understand the nature of that reading and how important it could be. I think if we had done that from day one, we would have had much better information and continue to do it. We also, at a certain point, we thought the scrubbers were as good as they were going to get. We stopped taking the samples, and we don't have as thorough historical data as a process engineer like me would like to see. As I mentioned in the last slide, I feel like I'm plugging for these online acid dew point monitors, but I really think that, if there was one thing about our systems that I wish I had, it would certainly be an online acid dew point monitor. This would help with both corrosion and lime consumption optimization. Really, really an important metric to be able to have. Chalmette backhouse and scrubber design. So the Chalmette system was installed 3 years to 4 years after the Lake Charles system was commissioned. At about the time when the Chalmette system was commissioned, we mostly had all of the problems with the Lake Charles system resolved. So it took us about 3 years to identify the source of all the corrosion problems, even understand that we had corrosion going on in the first place. It took us probably 5 years from the commissioning of the Lake Charles plant before we really had the system optimized and running very effectively. So that certainly takes a period of time to do that. Of course, there's always other priorities. This isn't our major process or our primary process. So the Chalmette baghouse was designed, or baghouse and scrubber design was designed with lessons learned from Lake Charles, considering the material handling issues, considering some of the flue gas flow issues we had at Lake Charles. So there were sort of two things that happened here. One, the leak air in the old baghouse was underestimated a bit. So because the baghouse was so old, we were drawing in a substantial amount of leak air. And we underestimated how much, or we overestimated the flow coming into the baghouse because there was so much leak air. That, and combined with that, we wanted to slightly over-design it just to make sure that there were no problems. We actually over-designed it a little bit too much. So the system was designed for a higher gas flow than what we typically had. That directly resulted in issues maintaining reaction tower differential pressure. So the reaction tower is a fluidized bed of lime. Without enough differential pressure, you will, what we call losing the bed, which is where, there's maybe 5 to 10 tons of lime in there that drops down to the bottom. All the lime has to be cleared out. You have to shut down the energy side of the plant until you can clean it out. It's really quite a problem. And at lower facility feed rates, this is happening more and more frequently. So we had to do a few things. We had to modify the bottom of the reaction tower to make it more practical to remove lime. We installed a screw conveyor and just a spent lime pan that allowed us to, instead of just dumping it out onto the ground of the facility and scooping it up, this is just a better way to handle it. We also have the flue gas recirculation duct, and we now open that damper all the way. So we recirculate the maximum amount of flue gas back into the entrance of the reaction tower to increase the flow as much as possible. But losing the losing the bed in the reaction tower is certainly a continuous event that happens at our facilities. And any plant with operation that can be inconsistent or that can see feed disruptions, et cetera, you could certainly see these problems as well.
Hey, Matt, we got a question. Apologies for the interruption, but we got a question. What type of flue gas flow measurement are you using? Is it actual flow meter or a calculation in the logic? What are you guys using?
Yeah, so we have a SEMS unit. So we actually have a flow meter put in all of our stacks. I think the problem was while we knew the flow at the cold stack, we didn't really know what the flow was at the inlet of the baghouse or the of the old baghouse before we had this system. So yeah, I mean, definitely recommend if you're going to install one of these things, accurately measure the flue gas coming into your baghouse at a wide variety of operational conditions, so you know pretty confidently what the flue gas flow is. So my last slide. So this would probably be 5 years after the Lake Charles system was installed, maybe 2 years after the Chalmette system was installed. We started to look at standard versus advanced hydrates. So these are applicable both in CDS and in DSI systems. We have DSI in another facility, but that's not the purpose of this presentation. We had issues with material handling bottlenecks, as I mentioned earlier. While we were improving the efficiency of our scrubbers, these were still problems at our higher sulfur feedstocks. And this was ultimately impacting facility throughput. Additionally, we had, of course, fresh lime cost is always a major issue, as is spent lime cost. So with more advanced hydrates, you're using less fresh lime, and while it costs more money, if you can see a large enough volume reduction, it can make sense to switch to these sorbents. Additionally, when you're using less fresh lime and you're using more as a percentage of the fresh lime, you have a lower volume of spent lime. So it reduces both your fresh lime and your spent lime costs at the right price point if you can see a good enough benefit. So we've spent a good amount of time in the last few years working with these different advanced and standard hydrates, and we actually found that the better and more advanced the hydrate, the more economically feasible it was for our processes across all of our sites. So for us, that was a really, really good solution, saved a lot of money. In some cases, it allowed our facilities to run at a higher feed rates. Overall, really, really helpful. And of course, the less material you're putting through these systems, the less issues you have with any sort of maintenance or wear and tear, et cetera. So I would certainly recommend to anyone installing a new system or anyone that has a system right now, if you have not looked at these advanced hydrates, would certainly recommend running trials and seeing if they make sense. At our system, we do not have a great way to project how much SO2 we're producing. So we typically rent an FTIR or equivalent to measure the SO2 inlet to the scrubber to make sure that we have a proper mass balance. As even modest improvements in efficiency of 5 to 10% can really make a big financial difference. And that's my last slide, so that's all I have.
Thanks, Mike. Just some follow-up questions, especially since we're on this slide and you're talking about spent lime. Lots of questions about what you guys do with the byproducts, with the spent lime byproducts, with the residues. Is that something that you can share with us, what Rain has done and how they've handled the spent residues?
Yeah, absolutely. So I want to say as of 3 to 4 years ago, we were landfilling these, which is more likely than not the standard. It was expensive, landfilling, what are you going to do? We really worked hard to find better outlets for these. And at this point, we have beneficial use permits at all 3 of our sites with emission control. And we find that year over year, as we keep looking for people that will take our spent lime, our costs are just going down, down, down. So now I would say per ton, our costs are down probably 70% from what they were 3 to 4 years ago. And we expect them to continue going in that direction.
Thanks. Any idea of what the end uses are for the spent material?
I know that one of our I don't know if I would call them a supplier, probably not, but one of the companies we were working with was using it to stabilize swampland in Louisiana. So he was using it to basically, go into a swamp, clear out trees, and build up the ground, which is, a really sloppy mud, and kind of solidify it. I've heard that they can be used for roads. Those are the two that I'm directly familiar with. I think there's a problem with the integrity, the structural integrity of it. It would be hard to build a large building on it, but if you're just paving a roadway or building a parking lot, something like that, I think it seems to be a good solution.
Thank you. We have a question all the way from India. Have you noticed any venturi throat erosion? And the second question there is, how much ash and salt recirculation per gas flow are you seeing?
Venturi, not that I'm aware of. We do look at the Venturi during all of our turnarounds. I'm not really aware of any physical issues in the reaction tower. As far as the spent lime recirculation, that's always tricky. There's really no good way that we can see to measure that. I would say, if I had to guess, our recycle ratios are probably in the area of 5 to 10 times the fresh lime injection rate. I don't know how to quantify that back to the flue gas flow. But it's one of those things where it's really hard to know for sure exactly how much spent lime you're recirculating. There's not a great way to measure it, unfortunately, that I'm aware of.
Thank you. One question that keeps coming up from new CDS users, folks that are installing new systems or getting ready to install new systems, what have been the best resources for you to learn about CDS operation and performance? And how do you make sure that your operations team stay up to date with any modern day advancements for in CDS operations?
Yeah, I think by the time I was working with these systems, we had a fair bit of in-house knowledge on exactly the important aspects to look at. Specifically, the reaction tower temperature is probably the most important aspect to look at, and that's the one that we have modified the most. It seems to be a lot of in-house knowledge. I met some people at the Dry Scrubber User Conference a few years ago, and I've continued relationships with them that have been very helpful. So certainly events like this, if there's any sort of networking aspect to this, would highly recommend going to that and talking to folks. And then, yeah, just research in general, how you learn about anything else. There's a lot of information online. As far as how do we communicate that to the operations folks, we do our best with our operating procedures. We try to continue to educate our engineers, have them go to events like this to see how these systems work.
Thank you.
Hey, Mike, this is Jerry. Great talk. Kind of triggered some questions as you're going through in my head that I wanted to present to you as well. You coming from a process engineering perspective, you mentioned the available lime index is one way that you look at the efficiency. From your perspective, how challenging with the CDS system is it to try to characterize the CDS scrubbing performance and efficiency, even using an FTR? How challenging is it using emissions data in general to really truly characterize the performance and to correlate with the available lime index?
Yeah, certainly. So from a mass balance perspective, we have found it immensely difficult. And every process is different, but the way calcination works is we effectively are reducing the mass. We're not combusting all of it. We're reducing the mass of our feedstock by about 25%, 25 to 30% as it goes through. We do not have real-time measurements of how much feedstock or how much final product we're producing. And we also lose a percentage of the sulfur in the feedstock that is burned off. So we really have probably maybe up to 20 to 30% error in projecting how much SO2 we're producing, simply from a theoretical basis. So that's the first real issue. And that's why when we do trials now, we bring an FTIR on site, we measure the CO2 and the SO2 and finalize the mass balance around the scrubber. So for us, that's a big issue, and would highly recommend, if you don't know really accurately what your SO2 production is, definitely bring an FTIR on site so you can measure it. That's the first issue. The second is just the nature of the CDS system. So because there's so much recirculation, it's really hard to tell on an hour-to-hour basis or even a day-to-day basis what the performance is. You know, we see trends where on multiple days our efficiency is improving, and then it'll reverse and decrease for multiple days. And it seems like you need at least a week of steady state operation. And then, as you mentioned, that presents an issue when you're, you know, only taking maybe one spent lime sample a day. You know, it's not always the best. So would highly recommend, you know, over time, just continuously taking samples, a few a week, if not every day, and getting a lot of good long-term data, just because there's so much process variability with these systems. It's not like a DSI system where you can run a trial for 24 hours and you kind of know what's going on. Did that answer your question, Jerry?
Yes, sir.
Mike, we've got a question about COVID-19. I know everybody all around the world is dealing with this. Have your plants experienced any impacts, positive or negative? And how are you dealing with those impacts as it relates to CDS operations?
I would say if there's one thing that it's not impacting, it's the operation of our CDS systems. Yeah, I mean, I don't really think it's a huge problem. You know, they're pretty good systems, you know, installed correctly. And once you kind of get them lined out after commissioning, they kind of run themselves for the most part. I mean, besides taking samples, you know, they're really doing their own thing, you know, unless something happens, like you lose the bed, you know, they do run themselves. I think the trick with them is understanding how to optimize the operation as opposed to dealing with them day to day.
Hey, Mike, this is Jerry again. You know, thinking more along the lines of what you were saying previously about the FTIR, and you know, you talk about the acid dew point monitor, which are great tools to have from a process perspective. Are there any different, whether it's new or a completely different instrument? Is there other instrumentation or data that you wish you had, so that you could, whether it's optimize performance or address just operations and maintenance issues? Is there any pieces of data that you feel like you wish you had that you don't have?
Yeah, I think the acid dew point is a huge one. I would definitely recommend loss and wave feeders to measure fresh lime consumption at any new installation. Knowing it's almost impossible to optimize these systems without knowing how much lime you're using on a regular basis. If you don't have that, probably the best you're going to get is lime shipments, which are not a great metric. So certainly acid dew point monitors, loss and wave feeders. I would love to have a permanent installation of SO2 and CO2 analyzers at the inlet to the reaction tower. That would allow me to do mass balances, you know, at any interval that I was interested in around the whole system. If I had those three things, I would be a pretty happy person, for sure.
Mike, we've got a question on buildup of material. Are there specific sections that has experienced the most buildup and corrosion over, let's say, the past year? And what do you think the primary causes are, and what remedies do you typically employ to fix those?
Over the last year, we've really got these things lined out. We don't really have corrosion issues anymore. The stack, as I mentioned, at Lake Charles had the highest corrosion. It was so bad we had to replace it after just a few years of operation. So the stack was the worst part we saw from corrosion. From a material buildup perspective, probably the reaction tower, just because of when we lose the bed a lot, we have issues and it kind of clogs up the venturi. We get some buildup that kind of spills out into the inlet duct. Material handling issues sometimes at the outlet of the bag house. We have some issues as well. I think that's probably the highest two areas of buildup.
Mike, this is Jerry again. You'd mentioned in one of your previous responses about loss and weight readings, and in your presentation, you'd mentioned your one of your units has solely a direct injection. So for the unit that's using direct injection, how are you guys estimating what your lime consumption is there, and do you have any perspective as to what you think the accuracy to that is?
Yeah, so of the three, we have two CDS systems, one DSI system. Of those three systems, we only measure the mass flow of lime at one of them. The other two facilities, we have really a spent lime silo percentage that we do not record in our DCS or historian systems, so I can't query that. And really what we use is deliveries. So it'll be fresh lime deliveries over a period of time. The problem, of course, with that is unless your system is operating very stably for weeks to months at a time, any disruption in operation, like if you lose the reaction tower bed, you have to inject a lot of fresh lime to rebuild the fluidized bed. And so that can completely skew any sort of performance figures. It's difficult. I would say it would be hard to have an accurate understanding of how much lime you're using over any higher resolution than like a week would be really tough. And that's also bad because, you know, there are times where we see, you know, what we think is high lime use for a few days and then it lines out. We don't really ever know. But yeah, I would definitely recommend if you can install loss and weight feeders or even load cells on the silo, something to measure the amount of the mass of lime that you're using.
All right, copy that. And
Travis, I'm sorry, Mike, we've got another question here. Is water injection definitely needed for improving reaction efficiency in the process?
Yes. Yeah. That's incredibly important. At our DSI system, we have temperatures around what the economizer outlet is, which is 350 to 400. At our CDS systems are running at low to mid 200s, and they're vastly, 2 to 3 times more efficient than our DSI system. It's incredibly important. Additionally, with CDS in general, our bag house is not designed, the bags in our bag house are not designed for the high temperatures, the outlet economizer. So from a design perspective, it's necessary as well.
all right, Mike, I know I've been hitting you with questions. I got one last one on my end. As you know, I know you didn't mention specifically, but I recognize, I know your facilities, one of the considerations for emissions compliance is around the NAAQS, which for those outside of the US, the National Ambient Air Quality Standards, as well as folks I've dealt with in the industry that's, you know, that's having to deal with that compliance rule. What kind of, because it's, as I understand, it's fence line monitoring and, you know, you guys may not necessarily be in a remote location. So, you know, can you speak to what have been the compliance challenges associated with any kind of fence line monitoring tied to your process, as well as ambient conditions like weather, and what's been your experience with that, with the challenges and the successes?
Yeah, so we the way we approached that was we modeled our emissions. And that's the way that it's recommended to handle it. So you effectively model your emissions and you make sure that whatever parish or county you're in is in attainment for the majority of the year up to whatever, you know, the government says they need to be in attainment for. The issue with it operationally is that we have internally found that concentration really seems to drive the dispersion of the SO2 itself. So temperature has a high impact, flow has a high impact, but what we actually control our stacks to is concentration. And that's an inherent problem because concentration is a function of both flue gas flow and mass flow of SO2. So running the systems controlling to a concentration for us has been quite a challenge, as there are certain situations where we have lower flue gas flows for whatever reason, and we really have to scrub a lot more SO2 than we otherwise would have. We've done a lot of internal work looking at relationships between the stack flow, temperature, whether it makes sense to run the CDS systems at a higher temperature to get better dispersion, so we have to scrub less. My opinion on that is that doesn't make sense. Although at some of our systems when we're not running out our cold stack, and we can run out of our hot stack, which is much higher, like 2000 degrees Fahrenheit, we really don't have to scrub anything because the dispersion is so good. So it's certainly a challenge, and if that's something you're going to be subjected to, you should do that modeling now before you design your systems. Because that was a really difficult for us to handle. And a lot of that drove the need to go to advanced hydrates, because with standard hydrates at some of our facilities, we would have had problems with material handling, or even just the capacity of the system just could not scrub that much. So definitely our most restrictive emission limit right now is the NACs over our permit. And that's been pretty difficult and expensive.
Thank you.
Yeah.
Mike, we've got one last question here from the audience. What typical SO2 reduction levels are you seeing from CDS and from the bag house, if you've been able to measure those separately?
I haven't. In our DSI systems, it's really tough. Just speaking anecdotally, I feel like control on the bags is maybe 20 to 30%, somewhere in that range. And in-flight capture is 70 to 80%. I would imagine that in a CDS system, the in-flight capture is much higher in the reaction tower, as it was designed for that. Again, anecdotally, not really speaking off any real data, I would have to say that probably 90+% of the SO2 is removed in the reaction tower. And we see that as our acid dew point coming into the reaction tower is probably around 280 F. The temperature leaving the reaction tower is 220 F, but we don't see any corrosion. So to me, that means the majority of the SO2 is being removed in the reaction tower, maybe have a small amount being removed in the bag house as well.
Thanks, Mike. Great presentation. Thanks for answering all those questions from the audience. There are no further questions from the audience, so I'm going to go ahead and turn it back over to Jerry. Thank you for your presentation, Mike.
No problem.
Yeah, thank you, Mike. I appreciate it. Yeah, it's been brought to my attention that you guys may not have seen the slides from the first go around on for our sponsorship. Believe that was on my end. I apologize. If you can't trust a guy with a banana shirt on to do two things at once, and who can you trust? So before I acknowledge other sponsors, I at least want to have a chance. Again, Gecko Robotics, certainly we discussed them as a sponsor for earlier before Mike's presentation, and I want to give an opportunity to show them, as well as Leckler, and for their support in the spraying community. We talk about nozzles specific to CDS. Obviously, it's integral to that process. National Filter Media, again, thank you for those guys, and integral to the CDS systems, obviously on the back end with the bag house. Obviously that's where folks like NFM and filtration comes in and is integral. So, and again, Mississippi Lime, as I mentioned them as a sponsor, obviously the integral to the CDS as well is going to be, your lime, which, as Mike discussed, between standard lime and enhanced lime can be an important consideration of which lime you use. So thank you to those guys. My apologies that, we didn't get those slides up there before, and hoping everyone is seeing them this go around. So I also wanted to thank and acknowledge some additional sponsors for the CDS webinar, and that have supported DSUA and the dry scrubbing industry. Lhoist North America, similar to Mississippi Lime, they're also a calcium provider. So, they're a subsidiary of Lhoist Group, who's a global limestone, quick lime, hydrated lime, silicate minerals company. So they've got they're a supplier of multiple high quality calcium products, including their Sorbical SP and SPS enhanced hydrated lime, which are used for acid control, for flue gas treatment for industrial as well as utility applications. In addition to that, Lilwas has a flue gas treatment team that has several decades of air pollution control experience. So they're there to provide custom support and solutions for end users to help them with compliance, optimization, as well as troubleshooting through a multitude of dry scrubbing applications. Primex, who's DSUA's newest sponsor, and thank you to them. Their name has been prevalent throughout DSUA over the years. Stuart Nicholson is one of the co-founders of DSUA from back in 2008, and they've been instrumental throughout all the years with DSUA, giving presentations and participating in breakout sessions. So they've been highly involved in the dry scrubbing industry. They provide comprehensive programs to help all dry scrubber users, whether it's a SDA or CDS or DSI, help the users optimize their overall performance. So these folks have a unique set of skills of all sorts of dry scrubber knowledge, technology, as well as mostly patience, which can be required to help, folks work through optimizations and troubleshooting. So, this has been evident in their 20-year track record of success working with these customers and helping them with their dry scrubbing applications. So if you're looking for optimizing performance, Primex will be folks that can be able to help you there. And lastly, Reaction Analytics Solutions. So this is a company that specializes in providing engineering solutions through their computational fluid dynamic or CFD modeling programs. Their founder, Dr. Guisu Liu, he's spent over 20 years working on not only fuel combustion processes, but also emission control technology developments, which has rendered over 100 CFD model engineering solutions. So whether you're looking at front-end combustion or back-end emission control, Reaction Analytics Solutions, they've got the CFD experience to be able to help you guys with this. So their unique CFD skill sets, kind of go above and beyond the conventional CFD developer. So they've incorporated chemistry modeling that can help optimize chemical as well as sorbent utilization by taking into consideration things like sorbent distribution and run various iterations to save you guys time doing it in the field. So their experience recently has been helped to fine-tune sorbent injection systems for acid gas and mercury abatement programs for dry sorbent and activated carbon injection systems. So big thank you to all those sponsors for the CDS webinars. Some of the other folks that are listed on here I'd like to recognize that didn't have slides was Carton Fujikin, as well as Graymont and RPM Solutions and United States Lime and Minerals. So a big thank you to all of our sponsors and everything you guys do to help support and drive the mission of collaboration and innovation, as well as working closely with our end users. So if anyone's interested to learn more about any of these sponsors, this was just intended to be kind of an introductory to what they do and what they do for the dry scrubber industry. So please feel free. Here's the link to dry scrubber users. You can find all the sponsors there, as well as click on their logos. It can take you to their website. You need to find out more information or get in contact with someone, feel free to go through dry scrubber users. We'll be happy to help facilitate that. So again, a big thank you and appreciate you guys listening and paying attention to our sponsors. And Ian, I'll turn this back over to you so that you guys can continue with Matt Wilson's presentation.
Thank you. Thanks, Jerry. I'd just like to remind the audience, please do submit your questions onto Slido. I will read them. If they're relevant during the presentation, I will interject when Matt's speaking and ask that question directly just for some clarification. All right. So Matthew Wilson is a pollution controls engineer with Tennessee Valley Authority, TVA. Matthew hired into TVA in 2000 and was stationed at the now demolished number 8 unit at Widows Creek fossil plant in northern Alabama. From the time he hired in, he's worked on pollution controls and support systems, starting with electrostatic precipitators and ash handling systems. Then he branched out to SCRs, anhydrous ammonia, acid gas abatement, both liquid and dry sorbent injection systems. In 2010, Matthew transitioned to corporate pollution controls type engineer. He was assigned to reverse gas and pulse jet baghouses, wet FGDs, and finally dry FGDs for project O&M and field support, along with site and field services peers. He will be providing today a plant report on the Alstom NID pulse jet fabric filter systems installed at TVA's Gallatin fossil plant that had first gas put through it back in 2015. So Matt, thank you for joining us today and presenting, and you can start when you're ready.
All right, thank you. Mic check and presentation screen check. Do I have the right screen up? Support.
You do, yes, sir.
All right, thank you. Again, my name is Matthew Wilson. Thank you for that introduction. Today we're going to be going over Gallatin fossil plants. We're going to have a plant update on Alstom's novel integrated desulfurization, or DID, dry scrubber. And before I start, just a sincere thanks to Gallatin's Mark Obrist, site engineer, and others on site whom have shared a considerable amount of info with me over the years. As Gallatin's learned the ins and outs of NID operation, couldn't have assembled this presentation without his and their at the plant cooperation, assistance, and input over the years. So, brief agenda. We've got overview as built. We've got several construction photos to share with everybody, and we'll go over how many assets we have on site. The performance and operation short section, and then a section that's always entertaining for opportunities. So jump right in. So Gallatin itself is located on the banks of the Cumberland River in Tennessee. As the crow flies, it's about 24 miles northeast of downtown Nashville, Tennessee. The original plant construction, not the air quality control system, the cost was about $138 million back in 1950s. Original first unit commercial operation was in November 1956. All the boilers on site are combustion engineering boilers, tangentially fired, pulverized coal units. We've got two different size boilers on site. The first two units have a nameplate rating, original nameplate rating of 300 megawatts and are about 1.7 million pounds of steam per hour. Units 3 and 4, the latter two units, have a nameplate of 327 megawatts and approximately 2 million pounds of steam per hour. Here is a terrific construction photo oversight view. On the far left is the powerhouse block itself. The brown and tan devices there, looks like buildings, those are around circa 1980 Moderator precipitators. Those were the particulate pollution control devices prior to the startup of this new air quality control system. They were completely bypassed as part of this project, thus supplying a full, or making the new air quality control system a full burden system, meaning all the fly ash generated from the boilers are carried over to the baghouse and dry scrubber, as well as the scrubber's byproduct itself. Thus, it's a full burden design. The fuel utilized for the air quality construction system design was a variety of fuel ranging from 100% Powder River Basin all the way up to a 50% Powder River Basin, 50% Illinois Basin. That's about 0.3 to 3.1 pounds of SO2 per million BTU range out of that full spectrum of fuel. The gas flow rates coming from the powerhouse block for units 1 and 2 are approximately 1.1 million ACFM, and for 3 and 4, approximately 1.15 million ACFM. Again, 3 and 4 are a little bit larger size than 1 and 2. The pulse jet fabric filter air to cloth ratios are around 3.03 for 1 and 2, and 3.29 for 3 and 4. And these details that I'm given, they're actually going to be on a later slide, the next slide, but I'm just repeating them here while you got something pretty to look at, which is this picture. So this will have more construction photos showing the overview. You can see there is a length of ductwork from the powerhouse block over to where the air quality control systems are, and what exists there physically is the discharge channel for the units. So we did have to reach across that discharge channel to make it to the new construction site. My instinct is to ask for questions at this time. However, I realize I'm not talking to people live out there. Although please do put in your questions online. Like I said, we've already gone over this information, so I'm going to skip over these type slides pretty quickly. All right, we got a good construction photo here. In the foreground, we've got our 4 pebble lime storage silos that are under construction, carbon steel. In the background, you see our concrete byproduct storage silos, flat bottom storage silos in construction. The pebble lime silos were supplied by Chemco through our Alstom air quality control system contract, and all of our byproduct transfer, conveyance, and storage system was supplied by United Conveyor Corporation. Inside, I just think it's a neat detail, the 10 paddle mixers that were selected, they are lined with Tyvar to keep this cooler byproduct, which is prone to sticking, from sticking so much in the 10 paddle mixers. During the construction of the pebble lime storage silos, these main storage silos, we did leave space for crushers. So our reagent specification now is pebble lime. It's sized 1/8 of an inch by 0 top size, but leaving space for crushers allows us to competitively bid pebble lime on the open market. Of course, we would need to go in with crushers, and then we could crush them on site. There are suppliers locally that can supply 1/8 of an inch by 0, so at present we don't have to run the crushers. Originally, we did have weigh scales on these pebble lime storage silos down at the bottom, and what they did is they measured the pebble lime volume or weight from the pebble lime storage silos over to the day bins located adjacent to the NID devices themselves. We had some issues with those, so basically during construction, startup commissioning, we did remove those. Another good construction photo, top down. Along with the project, we did install a new concrete stack. It has 4 separate flues inside that single stack. We did install new induced draft fans, 2 per unit, supplied by Howden Buffalo. So that is a key point. That means we've got 2 ID fans pulling, balancing the draft on these balanced draft boilers all the way through this entire system. We do not utilize booster fans. So that means that we had a high suction to really design these bag houses to, which was done successfully without any issues. In the background, again, you see progress had been made on the concrete byproduct storage silos, which are shown to the right of the stack, and the pebble lime silos were built, but they are hidden by the stack itself. This is a construction photo from the powerhouse block, standing by those old Moderator precipitators, looking towards the new NID dry scrubbers, bag houses. Unit 4's is on the far left, Unit 1 is on the far right. Everything's kind of brown, and I wanted to take a second to talk about weathering or corrosion protection and erosion protection that we went into with the design of this system. So TVA historically has used Core 10, which which used to be ASTM A242, weathering steel. They no longer make that. So we did specify ASTM A588, weathering steel construction. So it's basically a carbon steel product, but it has additional chemicals in it, chemistry, to assist with corrosion-based deterioration. So we were not worried too much about the unexposed steel during the construction. The bag houses and it itself, or specifically the bag houses, we did spec out a corrosion-resistant coating system. We did apply that. It's a spray-on, 3-part spray-on coating system. We applied it on the clean side of the tube sheet. We applied it 3 feet below the tube sheet and at the hopper bin line, or fluidized hopper trough in the bag house, and then the bottom third of the fluidizing trough.
Hey Matthew, we've got a question
Yes.
from the audience that I think is a good time to ask. This one comes from India, and the question is NID a modular system? Meaning, can you add modules as the gas flow capacity increases in a plant?
As the gas, well, I think that means like for a design construction phase. Alstom states that this is a modular type system. Yes, we've seen TVA actually visited several other sites during the selection process of which dry scrubber we were going to go with. They did not all look like this. They did not all have 4 modules, and I'm going to get into some good detailed photos of our modularization that we have. We have 4 inline NIDs, and they make them 4, they make them 6, they make them 8, they make them 10, they make them inline or coming down the middle and then branching off left and right. And so also, or GE now, they do advertise it as modularized. For us, we started out with a 5-module system and then would transition to a 4-module system during the design phase, which actually saved on some steel. Any other follow-up question to that?
No, I think that's
right.
it. Thank you. Thank you very much.
All right. As far as insulation, and I point this out because it's interesting and deals with corrosion. So our specification called for 4 inches of insulation. Alstom did comply with that, of course. The ductwork that you see in the foreground here has 4 inches of insulation. Anything hot had 4 inches of insulation, but then Alstom doubled the insulation on all the cold surfaces, so basically downstream of the scrubber. Why was that? Because they wanted to ensure that that metal stayed warm enough that it would not lead to acid gas corrosion attack during the operation of this unit. So we've got 8 inches of mineral wool insulation on all the cool surfaces, and that's an Alstom specification. Also, last thing for erosion, based on their experience, Alstom designed the inlet ducts of the J-duct reactor. So that's basically, actually, can you see my mouse on the shared screen?
No, it's not coming out.
Okay. All right.
Oh, maybe
maybe
we
I
can.
can see it. Yep.
Yeah,
There it
there
is.
you go.
Yep.
All right, thank you. Sorry for that inconvenience, everyone. So this is the inlet NID J-duct reactor, and this whole reactor, this is where the dry scrubbing takes place predominantly. This is lined on the interior with AR350 plate. That's abrasion resistant plate. It's not an ASTM standard, but that seems to have held up well during the operation to prevent erosion of this really particulate loaded area, high velocities and a lot of particulate going on right here in this reactor duct. So our design contract had already mentioned the 4 inline parallel NID reactor modules, meaning we go down, see if I can get my mouse on the screen. This is unit 3. This is the single inlet duct for unit 3. It goes down the full length, or you could say depth in this photo, all the way down. This is alpha module, and it goes Bravo Charlie Delta down the depth of that. So they're all in line, meaning flue gas wise here, inlet duct, and then parallel in flue gas flow. And the actual gas flow goes down. Here's a J. We'll see a good profile drawing in a moment. The inlet duct, the J reactor comes up this way, goes through the bag house, and then the flue gas comes out here. This is the outlet duct at the top. Then on the back side, hidden from view, it goes down to our ID fans, and then up to the stack. So each module reactor has a flow nozzle with pressure transmitters on either side, which is tuned to provide flue gas flow measurements. Each unit has 2 day bin reagent silos. That is snuggled in right in between there, in between Alpha and Bravo modules, in between Charlie and Delta modules. Unfortunately, I don't have a terrific picture of that angle. Each of the day bin reagent silos has 2 split variable speed screw trommel feeders on the bottom. So that's what meters the pebble lime flow over to the hydrators. And that metered flow was validated during our performance testing to be accurate enough. Each unit has 4 man-safe pulse jet fabric filter compartments with tandem louver dampers on both the inlet and the outlet with still air option. We designed this without any bypass dampers, so no baghouse bypass dampers. Our experience with bypass dampers is that they tend to leak. Over the years, we knew the particulate matter standards were getting stricter. Everything gets stricter on emission limits, so we did not want to run the risk of any bypass dampers leaking by. And each unit is equipped with its own activated carbon injection system. That's this silo here, and that was supplied by Norit via the Alstom contract. Here's an excellent side profile view from our TVA drawing. So again, this is from the back side, I guess, angle instead of those construction view angles. Here's our inlet manifold. Here's our venturi, which is essentially a flow nozzle of the flue gas. We got pressure transmitters on either side of that venturi section. And it took a lot of tuning with our TVA test crew giving information back to Alstom and with operations cooperation to figure out what accurate gas flows were going through here. Though the construction project was able to accurately tune this to say this much differential equals this much gas flow. You can see why it's called a J-duct. Goes up and then into the bag house. So this J-duct is the J-duct reactor, where the majority of the SO2 removal takes place. According to Alstom, 80% plus of their SO2 removal takes place in the J-duct reactor. Alstom says approximately 20% takes place across the bags. Just queuing in on some of the questions from last time. Has TVA validated that? We have not. We have not gone right here and tested SO2 removal across our J-duct reactor and across the bag house proper. This is the day bin pebble lime storage silo. Down here on this deck is where our hydrator and our mixers are. So the pebble lime discharges into the hydrator, has a little bit of water, swished around a little bit, it overflows into the mixer. The mixer takes byproduct, because we do recycle, so it takes byproduct, recycles that byproduct to take advantage of utilizing as much of the hydrated lime as possible. pebble lime converts it to hydrated lime, and then it overflows into the J duct. And it is a suspension dry scrubber system because it requires a minimum amount of flue gas through this J duct reactor to keep the product in suspension as it goes up. Obviously, if you don't have enough flue gas velocity, this is where all your byproduct ends up. Some ends up there anyway. This is a tiny little grit screw conveyor. It's not at the bottom, and it looks like a screw, and it dumps over into a small bin that our operations staff dumps periodically.
Matthew, I think now's the appropriate time to ask this question that we got. What about maintaining velocities at low loads to keep that fluidized? Do you have any issues with that?
So we have 4 of these in parallel, and what it's required, full load takes, at least on units 3 and 4, full load takes 4 of the modules to be in service. To keep it simple, if you come down to mid load, you take 1 module out of service. Now you have 3 in parallel in service. You come down to low load, you take another 1 out. Now you're down to 2 that are in service in parallel operation. So, and this is an automated process. Of course, it can be manual by the operators. Which modules come out of service as you come down on load and which modules go into service as you come up on load, those are operator selected, but it can, I think the effort is to keep it, the operational hours across all 4 modules relatively even. So for instance, sometimes they take Delta module out, and then Charlie, and then put those back in within the next time, or a month later they may be taking out Alpha and then Bravo to try to keep everything even wear and tear. So the gas velocity is maintained by taking those modules out of service. I think it required quite a bit of commissioning work to get that system to work in automatic, but I believe the dropout is relatively minimized now. That does not mean it's non-existent, but it is relatively minimized during those transitions, and we've got some performance graph that talks about what happens during those transitions. Obviously, during a transition, you have a period of time where your velocity is not up, the load is not up enough that it can maintain a suspension of dust. So there's a period where we see an SO2 spike, and we'll go over that.
One more question, Matthew. How reliable is byproduct removal from the bottom of the J duct? Any sort of air puffers or vibrators to promote material flow out of the duct into the conveyor?
All right, that's out of the bottom of the J duct, so that would be here. And this is a screw. No, there is no air puffers, nothing of that nature at all. This is, we got to remember, this is still warm, hot flue gas coming through here. It's had no water or moisture added to it. So it's still 300 degrees plus. Of course, the byproduct coming down is more on the order of 200 degrees Fahrenheit. Yes, there have been some problems with grit screw conveyor, but I believe in general, this works pretty good. Whenever we go in here, or the plant inspectors go in here, there is some product here. But in general, we do not have any bridging issues, do not have any bad problems removing this, the dropout. All right, this is a picture of our hydrator mixer deck. I kept things simple here. So you can see that the hydrator's on the bottom left. It's got some stick-on type insulation, some durable rubber type insulation, because converting or hydrating that pebble lime to hydrated lime is an exothermic reaction. So we really did that to protect the personnel. Alstom specified that to protect the personnel. Up on top, you see the screw feeder. It's not the trommel screw feeder that meters the trommel feeder goes into this screw feeder, and it just simply transports the pebble lime to the correct side of the hydrator. And then on the top right, we see that the fluidizing trough's byproduct outlet valve is resting right there. We only have one of those per unit, no, per module, one outlet valve per module. So what's out of the picture is one mixer per module, one J-duct mid-reactor, which we've already gone over well, one activated carbon injection lance per module, one long fluidizing trough with that one byproduct valve. That fluidizing trough is slightly tilted towards this side, towards the hydrator mixer side. And we put warm air up through the bottom of a fluidizing air cloth. And in general, we do not have any issues with moving that fluidized byproduct. It tends to feed well out of the single outlet valve, and it tends to feed well out to the 4-meter wide recycle rotary feeder. The recycle rotary feeder is how we meter the recycle product rate back to the mixer. Now for performance operation. So performance guarantees the maximum SO2 emission was 0.12 pound of SO2 per million BTU. The system met all performance guarantees for SO2, filterable particulate matter, mercury, sulfuric acid, hydrochloric acid, and opacity. The NID reactor requires the minimum gas flow. We already talked about that prior to admitting the hydrated lime or recycle. So I've got another slide on that. And we already talked about by design, this results in some short SO2 spikes when taking the modules out of service and placing in service. I also added a couple more notes, basically from the last presentation. So at this system, we are required to continuously monitor our SO2, our opacity, our flue gas flow, and our mercury. We do that with stack flue mounted CIMs, continuous emission monitoring systems. We do not have particulate matter CIMs. We only utilize opacity monitors, which does an excellent job and identifies bag leaks quickly, even minor bag leaks, minor bag spikes, bag leak spiking. During the Alstom tune-up phase during startup, scrutiny for proper process water pressure and flow took place in order to minimize the J-duct dropout to that grit conveyor that we were talking about. That took a lot of time to balance out that water pressure, water flow to prevent the dropout. I think we have a moisture analyzer that doesn't really get discussed that much. It's on the back end in the common outlet duct of each unit's dry scrubber. We do not have an online SO2 point monitor.
Matthew, just a friendly reminder, about 5 minutes left.
Super, thank you. All right, here is our performance. What are we doing? We are placing a module into service, and it takes about 15 minutes for this transition. Item number 1 is our SO2 that does spike up during this transition and then readily climbs back down. Now some opportunities. So pebble lime silos, live bin bottom, we had known failures prior to the final design, so this was discussed, talked about modifying the stainless steel bands, ribs on expansion joints. Gallatin has failed 3 of the 4 expansion joints, even with precautions made during the design phase. So basically it's a high priority inspection route by our operations. Gas flow nozzle, pressure indicating transmitters, that's in the inlet duct. Originally all the measuring sample tubing was gained together, so the lesson learned there, that did not provide for good accuracy, so we had to go back with individual sampling tubes. Opportunities, you can see on the far right, this is on the clean side of the tube sheet of our bag house. That is a big pile of spray-on coating system down below. That's the spray-on coating system dripping off our structural steel. This is something that's supposed to be about 10 to 12 mils thick. So opportunity there is not everyone can apply on-site corrosion-resistant spray systems, and specify 5 years minimum with experience, and preferably make it sure that it's their line of work, not a side job. This is an easy one. Pebble line conveyor lines plug without adequate airflow. We learned this. So here was the intake filter. It's 11 feet above the ground. It's hard to get a change out on this, and it's hard to tell when it needs changing. So this is where Gallatin moved it to. Now it's nice and accessible down at the bottom, and you can see the differential across this air intake when the manual differential gauge pops. That mixer hydrator, brand new one, is on the left. This is the internals of Alstom's hydrator design. This is considered the mixer area of this hydrator mixer. This is what it's not supposed to look like when it's plugged. So there are opportunities that Gallatin learned on the nozzles, and basically this is a close-up view of the nozzle. It has a shielded, this is the nozzle tip, and they ended up putting a stainless steel O-ring between the bushing and the nozzle tip, and then tack welding everything to keep the nozzle from rotating out of position. 4-meter wide mixer unloader, construction photo. So basically we had some bearing seal design leak issues on these that Alstom took care of with a rebuild and came back with an 1.5 inch longer shaft. And then opportunities, we do have 10-meter length bags with cages. I thought this was interesting. Here's 4, you can see them installed in the tube sheet right beside each other. And then here's 3, and then 1 way out over here. So I had done this, I attached a string, and with essentially no effort whatsoever, was able to pull this a good clear 6 feet away with no effort whatsoever. So what we're getting at there is it does not take much to move around a 10-meter length bag and cage combination. So we have experienced some issues with that. That's a whole nother presentation on our bag house experience. But long story short, a NID design bag house can experience flue gas distribution turbulence. And our recommendation is to scrutinize CFD analysis of both particles and flue gas flow and direction and velocity inside the bag house itself. And so we've gone over overview, as built, performance operation, and some opportunities. Any additional questions, gents?
Thanks, Matthew. That was a great presentation. I think we really got a lot of insight into the system that you guys have. We've asked a lot of questions from the audience throughout the presentation, so thanks for bearing with me for those interruptions. Just a couple of general questions. I'll ask the same question about COVID-19 and impacts to Gallatin and operations there. How have you guys been dealing with those?
I am stationed in corporate, but just in general, TVA has been keeping a close eye both on other utilities and cases within our region, within a Tennessee Valley. We do have restricted travel outside the Tennessee Valley, and on site at our plants, we enforce mask requirements to be worn. We have self-observation check forms to be filled out by all plant employees and contractors prior to coming on site every day. We have, of course, hotlines set up, nurses on standby, police, the TVA police engaged to answer phones. If there's, and basically the general communication is, if there's any doubt, if you're feeling sick at all in the slightest, call. We'll work through it, and stay away if you are sick. There has been some cases of employees that's been diagnosed with COVID-19, and then some segregation as a result, but no major impact to operations. that I am aware of. I need to put that disclaimer on there since I'm a lowly engineer.
Hey Matt, this is Jerry. One common as a lime supplier, one common question we tend to get from a lot of folks are, what kind of lime silo size should I have? Like, how many days storage should I plan for with like say a new design? What's been your guys' experience for how many days storage you guys designed for, and any thoughts to and feelings is that what you guys designed for was appropriate, or do you guys have different input on what you think folks should design for?
Copy that. So basically the question's how do we go about sizing our lime storage silos? I was involved. I had the opportunity to be involved in that during the design phase. It was a surprisingly highly eventful debate on how to handle that. First of all, where are your products coming from? How do they get there? That was discussed. For here we have what is the weather conditions around all year? All that factors into how much product you should store on site. For us, we ended up with 4 total silos up there that we showed earlier, and 2 silos supply 2 units. Basically, they are cross-tied. Only one is the normal feed for each unit, but they are cross-tied. Each of them is around 10,000 cubic feet. It's sized to store 30 hours worth of pebble lime at a 75% PRB, 25% Illinois Basin blend. And then each day bin is also sized to store 30 hours of pebble lime. So this really adds up over the days, and that hours is full load operation, 20 for that full 30 hours, which in reality does not happen that often. We run full load and then we can run low load. And of course you can always run low load if you run into a supply issue to stretch out your storage capabilities.
Thank you.
Matthew, we have one last question, or time for one more last question before we turn it back over to the DSUA organizers. The question is, do you control your scrubber based on outlet temperature, or do you use the humidity sensors and control on approach to dew point?
Operations operates to, we've seen it 2 different ways, but around 200 or 210 degrees Fahrenheit for 100% PRB fuel, and for 15% Illinois Basin fuel, we operate to about 190 degrees Fahrenheit. So the answer is the outlet temperature. It's the way that we do that, and constant monitoring of the dropout into that J-duct reactor into the grid screw.
Thank you. With that, Matthew, thank you very much for the presentation. The pictures were terrific, especially through the construction phases, really insightful. Jerry, I'm going to turn it back over to you to wrap us up.
Yes, sir. I just wanted to kind of wrap this up. I know we're coming up to our 11:30 time limit, and I just wanted to wrap up first off by saying thank you to our presenters, both Mike and Matt. Can't do this without folks kind of stepping up and giving their time and some effort to put this together. So certainly we appreciate your guys' efforts and participation. Thank you to Ian for being our moderator, kind of keeping things together. We certainly appreciate that. I also want to again recognize and thank our sponsors for not only the sponsorship for this webinar, but their continued participation in the dry scrubber industry. And for those of you who are still viewing, please recognize below the streaming window. If you guys, there's also information about the sponsors there, and you can get redirected to their websites as well and learn a little bit about them. And also want to say thank you to the DSUA board members. While I'm one of 7, there's also Travis Reynolds of GE, Sean Vierink of RPM, Craig Henry of AEP, Dave Kahn of Gecko Robotics, Kurt Bean of Mississippi Lime Company, and Wes Painter of Eastman Chemical. These folks, everyone's volunteering their time to be actively engaged in part of the DSUA board to kind of pull all this together throughout the year. And so there's a lot of things going on in the background scenes that these guys are all supporting and making happen. So, couldn't do this without you guys. So appreciate that. And for those of you guys that logged in to view, certainly appreciate your participation. Thank you for sending in the questions. And if anyone has any additional questions that they thought of afterwards, or maybe they didn't get answered, certainly we'll work with our presenters to ensure that we try and get every question answered and out there to everybody, some form of a response. And certainly if anyone has any feedback, what did you like about the webinar? What could be better? Is there anything specific you'd like to hear about any of these topics that you didn't hear? Anything whatsoever, please feel free to send that feedback through to the DSUA website or even the LinkedIn page, whichever is the most convenient way for you to get the information back to us. We certainly appreciate that feedback. So once this recording is uploaded, we'll distribute. So if you guys want to share, we certainly appreciate that. Follow the DSUA LinkedIn page is another way to see updates, and otherwise we'll continue sending out some emails. And be on the lookout for announcements on the next DSUA webinar. We expect some time in November. We'll get this one done. This one will be on the dry sorbent injection technology. So be on the lookout. And again, thank you to everybody. And we look forward to your participation in future webinars. Take care and stay safe.